Welcome to Late Night History. Settle in. There is no hurry here, and nothing tonight will ask anything of you. You can let your shoulders drop away from your ears, let the weight of the day sink down into the mattress, and let your breathing find its own slow rhythm. Because the story I am going to tell you is a long one, and a gentle one. And it does not matter at all if you fall asleep somewhere in the middle of it. It is a story about something enormous and quiet, something that has been there under your bed and under your feet and under every place you have ever stood, all your life, moving so slowly that you have never once felt it. And the strange thing, the thing that makes this worth a whole long night of telling, is that for a very long time even the people who study it did not picture it correctly. Not really. They had a picture, a tidy picture, one you were probably shown once on a poster in a classroom, and it turns out that picture was almost exactly backwards. Let me begin with the moment the picture changed, because it changed recently, more recently than you might think. In February of 2023, a study appeared in the journal Nature. Its title was long and careful, the way scientific titles are, and it read, "Asthenospheric low-velocity zone consistent with globally prevalent partial melting." The names on it were Junlin Hua and Fischer and Thorsten Becker and their colleagues, working out of the University of Texas Institute for Geophysics and out of Brown University. And what they had done was this. They had gathered together a great mountain of records, the traces of countless earthquakes as read by instruments all over the world, and they had woven those records into a single map. A map not of the surface of the earth, not of coastlines or mountains or the shapes of the countries, but a map of something hidden. A map of a layer. The layer sits about 150 kilometres beneath the ground, 150 kilometres down. Try for just a moment to feel how far that is, though feeling it is almost impossible, and that impossibility is part of the wonder. If you could somehow drive straight down, straight into the earth, on a road that went nowhere but down, at the speed you might take on an open motorway, it would still take you well over an hour of driving to reach it. Down through the soil and the roots, down through the bedrock, down past the deepest mine any human being has ever dug, and then down again, many, many times further than that, into a darkness and a heat that no drill has ever touched and no eye has ever seen. And there, at that depth, spread out beneath nearly the entire surface of the planet, they found a film. A thin, nearly worldwide film of rock that is not quite solid and not quite liquid. Rock that is partly, faintly, melted, a global film of partial melt. That was the discovery. Not a lake of fire in one place. Not a scattered handful of hot pockets here and there under the volcanoes, which is roughly what people had assumed before. But something close to a single continuous underlayer, a shared, soft floor, running beneath almost all of the great plates that carry the continents and the oceans on their backs. Earlier thinking had treated that melt as patchy, as regional, as a local thing you might find in one spot and not another. The surprise of 2023 was how continuous it looked, how global, as though the whole rigid shell of the world were resting on one thin, shared, half-melted sheet. And you would think, wouldn't you, that finding such a thing would settle matters, that here, at last, was the hidden cushion, the greased layer, the reason the continents can drift. Here was the thing sliding the plates around, the slippery film beneath the raft. It would make such a neat story. But that is not what they found. And this is the part I want you to carry down into sleep with you, because it is the quiet heart of the whole night. When Hua and Fischer and Becker looked at where the melt was and how much of it there was, and then compared that against how fast the plates above it were actually moving, the two things did not match. They did not line up. There was no clean relationship between the amount of melt beneath a plate and the speed of that plate across the world. The melt was there almost everywhere, this near global film, and yet, statistically, it did not seem to be the thing deciding how fast the continents drift. The lead author put it plainly, in a way that has been quoted many times since. The melt, he said, turns out to not influence the motion of the plates. It may be a passenger, not the engine. A real thing, a genuine layer of partly molten rock wrapped around the inside of the world, and it appears to be riding along rather than driving. So the picture you were probably given, the picture of solid continents floating and sliding on a slippery molten ocean, is wrong in two ways at once. It is wrong about what the layer is made of, as we shall see, because the layer is not an ocean and is not molten in the way you imagine. And it may be wrong about what the layer does, because even the real melt that is truly down there does not appear to be the thing greasing the wheels. Nobody, it seems, had quite pictured it right. Not the classroom, and until recently, not even the field itself. Now, before we go down into it, and we are going to go down into it slowly over this whole long night, layer by layer, until you understand this hidden place better than you ever expected to, let me do one small thing, the way I always do. I would love to know where in the world you are listening from tonight. Somewhere the ground beneath you is doing exactly what I am describing, moving without your knowledge, carrying you a hair's breadth further from where you were yesterday. So if you feel like it, whenever it suits you, leave a note and tell me where you are. A country, a city, a quiet room. And if you are new here, and you would like more slow journeys like this one, you might gently subscribe. So the next long, quiet story finds its way to you on the next night you cannot sleep. That is all. You do not have to do any of it. You can simply lie there and listen and let the words carry you down. Because that is what we are going to do. We are going to descend, together, at the slowest and gentlest pace, into the layer that lets the world move. And I promise you it does not matter where in this story you fall asleep, because the layer will still be there in the morning, doing what it has done for billions of years, and you will not have missed a thing that cannot wait. So let us begin the descent properly, and let us begin it by clearing away the wrong picture gently, the way you might clear a fogged window with the flat of your hand, so that we can see what is actually there. Here is the picture you were probably given. Somewhere, in some room, when you were young, there was a diagram, a cross-section of the earth, sliced open like a piece of fruit, showing rings, a thin skin on the outside, labelled the crust, the part we live on, the part with the mountains and the seafloor. And then, just beneath it, a band, and in almost every version of that diagram, that band was coloured red or orange, a hot, angry colour, and it was often drawn to look like a sea of molten rock. And the story that went with the picture was simple and memorable, which is exactly why it spread so far and lasted so long. The continents, the story said, are like great stone rafts, and they float on this hot molten sea, and they drift across it slowly, the way a leaf drifts across the surface of a pond. It is a lovely image. It is easy to hold in the mind, and it is, unfortunately, almost entirely wrong. The layer beneath the plates is not a sea. It is not a molten ocean. It is not lava in the sense you are imagining, not a glowing liquid you could pour, not a fluid the plates bob and float upon. The layer is rock, solid rock. Overwhelmingly, stubbornly, more than 99% solid rock. If you could somehow reach down and take a piece of it in your hand, you could not, of course. The heat and the pressure would not allow it, but if you could, you would not be holding a handful of liquid. You would be holding stone. Hot stone, yes, stone under unimaginable pressure. Stone that behaves over the enormous stretches of time we will come to in ways that stone at the surface never does. But stone, all the same. Not a puddle, not a pool, not a sea. Let me sit with that for a moment, because everything else tonight rests upon it, the way the plates themselves rest upon the layer. More than 99% solid. The tiny fraction of true melt that the 2023 study mapped, that near global film we began with, is exactly that, a tiny fraction. Well under 1% in many places, up to at most a few percent by volume, even where it is most present, which means that even in the parts of this hidden layer that are described as partly melted, the rock is still overwhelmingly solid. The melt is not the main event. The melt is a whisper, a trace, a faint smear threaded through a body of stone that remains, by any honest accounting, solid rock. And so the whole comfortable image collapses, the raft and the molten sea, and we are left with a much stranger and much more interesting truth, which is this. The continents do drift. That much is real, and we shall honour it all night. But they do not drift because they are floating on a liquid. They drift because the solid rock beneath them can, given enough time, flow, solid rock. Flowing, not melting into liquid and pouring, but staying solid, and yet, over ages so long, the mind slides right off them, creeping, deforming, moving like something between ice and stone and cold honey. That is the real hidden cushion, not a molten sea, a layer of solid stone that has been made just soft enough, just weak enough, to give way slowly beneath the weight of the world above it. And here we arrive at the name of the thing which I have been holding back, and which I want to give you now, slowly, because the name itself tells you almost everything. The layer is called the asthenosphere. Say it to yourself, if you like, the way you might turn a smooth stone over in your fingers in the dark. Asthenosphere, it comes from Greek. The root asthens means, quite simply, without strength. Weak, the weak layer. The sphere without strength. It is a beautiful and honest name because it does not describe what the layer is made of, and it does not describe how hot it is or how deep it lies. It describes what the layer does, or rather what it fails to do. It fails to stay rigid. It fails to hold its shape against the slow, patient pressures working upon it across the ages. Above it lies the strong layer, the rigid shell, the part that holds together and cracks into plates and carries the continents, and that layer has its own name, the lithosphere, from the Greek for stone, the stone sphere. And beneath the stone sphere lies the weak sphere, the strong shell, and under it the yielding layer that lets the shell move. Lithosphere above, asthenosphere below. The strong and the weak, stacked one upon the other, all the way around the world. And what I find most quietly astonishing about that name, the weak layer, is when it was given. Because you might assume, given that this is a story about drifting continents and moving plates, that the name came along with the whole grand theory of plate tectonics, that great revolution in how we understand the Earth. But it did not. The name came first, long first, decades first. The word asthenosphere was coined in 1914 by a geologist named Joseph Barrell. 1914. Sit with that date for a moment, in the quiet. 1914 was a world without the theory that would eventually make sense of all this. In 1914, the idea that continents could move, that they could drift across the face of the earth over millions of years, was not accepted. It was barely even proposed. The evidence that would eventually convince the world would not arrive for another half a century. The Great Acceptance, the moment when the scientific community finally agreed that yes, the plates truly move, would not come until the 1960s. And yet here was Joseph Barrell, decades earlier, in a world that did not believe continents could move at all, reasoning his way to the conclusion that there had to be a weak layer down there, a soft cushion beneath the rigid crust, something that could yield, something without strength. He did not reason his way to it from the drifting of continents, because that idea was not yet his to use. He reasoned his way to it from something else, something patient and clever. He looked at the way the surface of the earth behaves under load. He thought about how the crust bends and adjusts when great weights are placed upon it or lifted from it, the way the ground rises, ever so slowly, over thousands of years after a vast sheet of ice melts away and stops pressing it down. And he understood that for the surface to behave that way, for it to sink under a load and rise again when the load is gone, there had to be something beneath it that could flow, something that could get out of the way and then, slowly, flow back. A rigid shell alone could not do that. A rigid shell, sitting on more rigid rock all the way down, would simply hold its shape. For the crust to float and adjust and rebound, it needed to be resting on something weak. And so he named that something, the weak layer, the asthenosphere. In 1914, before the drifting continents had their theory, a man gave a name to the soft floor of the world simply because he sensed, from the way the ground breathed under its burdens, that the soft floor had to be there. I find that a comforting thing to think about as the night settles, that the understanding came in pieces, out of order, a name arriving decades before the story that would need it. That a person could sense the presence of a hidden layer 150 kilometres down in the dark, not by seeing it, not by touching it, not by drilling to it, but by watching the slow rise of land freed from ancient ice, and reasoning that something soft must lie beneath. The weak sphere had a name before the world was ready to believe in the thing the weak sphere makes possible. So let us hold the true picture now, clearly, before we go any deeper, and let us keep it with us all through the descent to come. There is the lithosphere, the stone sphere, the rigid outer shell of the earth, broken into great plates, carrying the continents and the ocean floors upon it. Cold and strong and stiff, this is the part we live on. This is the ground you are lying above right now. It feels, to us, like the very definition of solid and permanent. The bedrock, the unshakable, and on our timescales, on the scale of a human life or even of all human history put together, it very nearly is. And then, beneath it, there is the asthenosphere, the weak sphere, not liquid, not a molten sea, not a pool of lava the continents float upon, but solid rock, more than 99% solid, that has been made soft, made weak, made yielding, so that it can flow imperceptibly over the vast reaches of geologic time. This is the hidden cushion of the title, and you can already feel, I hope, how much stranger and how much more beautiful it is than the classroom picture. Not a fire beneath a raft, a slow, solid river of stone, flowing without ever quite melting, and letting the whole rigid shell of the world creep across its surface at a pace no human sense could ever detect. The layer sits, roughly, between about 80 and 200 kilometres deep, though its edges wander from place to place, thicker here, thinner there, higher in some regions and lower in others. The way the depth of any real thing in the real world refuses to hold to a single tidy number. And the melt, the true partial melt that the 2023 study mapped, that near global film, sits down around the 150-kilometre mark, threaded through the solid rock as the faintest of presences. A film within the weak layer, a whisper within the cushion, and already the questions begin to gather, the way questions do in the dark when you are almost asleep and the mind wanders freely down into things. If it is not liquid, if it is solid stone, more than 99% solid, then how, in any sense that means anything, can it flow? How can something solid move like a fluid? What does it even mean to say that stone flows? A block of stone on your windowsill does not flow. A pebble in your hand does not flow. So how can the rock 150 kilometres down be solid and flowing at once? That is a real question, and it has a real and beautiful answer, and we will come to it slowly, in its own time, further down the night. Hold it gently. Do not chase it. Let it wait. And another question, quieter still. If the layer is 150 kilometres down, deeper than any drill has ever gone or ever will go, deeper than the deepest hole ever bored into the earth by many, many times over, then how does anyone know it is there at all? How did Benno Gutenberg and later Hua and Fischer and Becker come to map a place that no one has ever visited and no one ever will? How do you draw a map of a layer you cannot see, cannot touch, cannot reach, that lies in a heat and a pressure that would destroy any instrument long before it arrived? That, too, has an answer, and it is one of the loveliest parts of the whole story. Because the answer is that we read the layer in the echoes of distant earthquakes, in the way the shudders of the ground far away slow down as they pass through the weak sphere. The whole map is written in echoes, but that, too, can wait. Let it wait. For now, all I want you to carry down with you, as the first weight lifts from the day and the room grows soft around you, is the simple overturning of the old picture. The continents do not float on a sea of fire, they rest on a layer of solid stone that flows. The hidden cushion is real, but it is not molten in the way you were told. And it is over 99% solid, and its true name means, simply, the weak layer, and that name was given by a man in 1914 who sensed the softness of the deep world from the slow rising of land that ice had once pressed down. And even the faint film of real melt that hides within it, the near-global film, mapped only in 2023, appears against every expectation. Not to be the thing that moves the plates at all. The engine, then, is somewhere else. The mover is something else. And the melt, the cushion, the soft floor of the world may be riding along quietly, a passenger on the great slow machine, rather than driving it. We will find the true engine before this night is through. We will go down and down, through the solid rock that flows, through the trace of water hidden in the crystals that makes the whole thing possible, through the echoes of earthquakes that let us see in the dark, all the way to the cold, heavy, sinking slabs that may be doing the real pulling. We have a long, slow way to go, and there is no rush at all. But before we take another step downward, let me linger here a while longer, at the surface, in the ordinary world, because I think it helps to stand for a moment at the top of the stairs before you begin to descend them. Think of the ground beneath your bed, the floor, the foundation, the soil, and then the rock beneath the soil. It feels utterly still. It feels like the very model of stillness, the thing all other things are measured against. When we want to describe something as permanent, as unmoving, as dependable, we say it is solid as bedrock, set in stone, on firm ground. Our whole language for certainty and safety is borrowed from the ground beneath us, because the ground beneath us seems to be the one thing that never moves. And on the timescale of your night, it does not. That is true, and it is worth saying gently, so that no part of you feels unsettled as you drift off. Nothing beneath you will move tonight in any way you could ever feel. The rock is, for you, for this night, for your whole life, as still and as solid as it has always seemed. You are safe. The ground is holding. It will hold until morning and long, long after. But on another clock, on the Earth's own clock, the vast slow clock that ticks in millions of years rather than in minutes, that same still ground is not still at all. It is moving. It is flowing. The plate beneath you is drifting, carrying the whole landscape you know across the face of the world, and beneath that plate the weak sphere is creeping, yielding, flowing like the slowest river ever imagined. The continents are travelling. They have travelled before. The land you are lying above tonight was, in ages long past, somewhere else entirely, at some other latitude, under some other sky. And it is still travelling now, tonight, as you fall asleep, at a pace so slow that in the whole length of a human life it would move you only a matter of meters. But it is moving. The bedrock, the byword for stillness, is in truth a slow river, and you are floating down it, and you have been floating down it your entire life, without ever once feeling the current. That is the paradox we will spend the whole night dissolving, gently, until it stops being a paradox and becomes instead a kind of peace. Solid and flowing, still and moving, permanent and always leaving. The words solid and liquid, it turns out, are not quite the fixed opposites we imagine them to be. They are more like descriptions of patience, of how long you are willing to wait. Wait a second, or an hour, or a lifetime, and the rock of the weak sphere is solid, unquestionably solid, stone you could break your hand against. Wait 1,000,000 years, 10 million, 100 million, and that same stone flows like a river. It was never a question of what the rock is. It was always a question of how long you watch it. And I think there is something in that worth taking down into sleep with you, something almost tender. That the hardest, heaviest, most unmoving thing you can imagine, the solid rock of the earth, is, on a long enough patience, a flowing thing. That nothing is quite as fixed as it appears, and that this is not frightening, but rather, somehow, gentle. The world softens if you are willing to wait. The stone gives way, the mountains flow. Everything that seems set forever is, on the earth's own unhurried clock, quietly on the move, quietly becoming something else, quietly flowing on towards somewhere it has not yet arrived. So let that be the ground we stand on, at the top of the descent. The old picture, cleared away, no molten sea, no floating rafts, no lake of fire beneath a stone raft, and the true picture, set gently in its place, a rigid shell of stone, the lithosphere, resting on a weak layer of stone that flows, the asthenosphere, whose very name means without strength, named in a world that did not yet believe the continents could move. A near-global film of the faintest partial melt, threaded through that weak layer 150 kilometres down, mapped only in 2023. And carrying with it a quiet surprise that it does not, after all, appear to be the thing that moves the world. The engine is elsewhere, the river runs on. and we have all night to follow it down. Let your breathing slow, let the picture settle. There is the ground, so still beneath you, so solid, so safe for tonight. And there, far below it, in the warm dark, is the weak sphere, flowing without ever melting, carrying you a hair's breadth onward through the night, as it has carried everyone who has ever slept on this drifting, quiet, gently moving earth. We have only just reached the top of the stairs. The way down is long and soft, and it begins with a question we have already touched, the strangest and simplest question of all. The one we will answer slowly next. How? If it is solid stone and not liquid at all, can the rock down there possibly flow? The question deserves a slow answer. And the slow answer begins, as so many answers about the deep earth do, not with fire, not with eruption, not with anything dramatic at all, but with something almost embarrassingly ordinary, with ice. Think of a glacier. Not the edge of one, carving into the sea with a sound like cannon fire, not the dramatic part that gets filmed and put on the news. Think of the interior of a glacier, somewhere deep in its blue-white body, somewhere in the middle of Greenland or high in the valleys of Antarctica, a place no human has ever stood and likely never will. And think of what the ice is doing there, in that unvisited interior, in the cold and the pressure and the absolute dark of the middle of a continental ice sheet. It is doing nothing you could watch. It is doing nothing you could film. It is moving, yes, but at a rate so glacial, and we use that word now as a synonym for barely perceptible, for so slow as to be almost meaningless to a human eye. And this is exactly right, at a rate so glacial that in the time you spend reading a single page of a book, the ice in the interior of Greenland has moved a distance roughly equivalent to the width of a human eyelash. It is stone slow. It is geologically slow, and yet it moves. And it moves not by melting. That is the thing to hold on to. The interior of a glacier is solid ice, frozen through, not a hidden river of liquid water making its way down a secret channel. The ice in the deep interior of a glacier is solid, and it flows anyway, because the crystals of ice, and ice, like rock, like olivine, like almost every mineral on Earth, is made of crystals. Those crystals can deform. They can change their shape without losing their solidity. The atoms inside them can migrate. The tiny defects and dislocations in the crystal lattice, the places where the orderly pattern of atoms has a gap, a step, a vacancy, those defects can travel through the crystal, grain by grain, and as they move, the crystal itself slowly shifts, slowly yields, slowly flows, without ever ceasing to be solid. Not a melt, a creep. This is the word the scientists use, and it is a good word. Creep. It carries exactly the right sense of slowness, of the almost imperceptible, of something happening so quietly and at such a pace that you would never notice it in a human lifetime, but that, given the Earth's own kind of time, adds up to continents moved, mountains built, ocean basins opened and closed and opened again, solid state creep. The rock creeps, the crystals deform without breaking, the atoms move without the whole becoming liquid, and this is how the asthenosphere flows. Down at 150 kilometres, in the warm dark of the upper mantle, the rock is peridotite, a dense, heavy, greenish rock made overwhelmingly of the mineral olivine. If you have ever seen a piece of jewellery set with the pale green gem called peridot, you have seen olivine. The gem and the deep mantle rock are made of the same mineral. One is cut and polished and worn in the light, and the other sits in the dark at temperatures approaching 1300 degrees Celsius and pressures tens of thousands of times greater than the atmosphere at the surface. And it glows, if you could somehow see it, a dull and steady red, not the bright orange red of an erupting volcano, but the banked ember red of something that has been hot for 4 billion years and will be hot for billions more. It glows in the dark, solid and slow and ancient, and it creeps. In the olivine crystals of the asthenosphere, 2 varieties of this solid-state creep are at work. And they are worth understanding slowly, because they are the engine of the whole thing, the real answer to the question of how solid stone flows. The first is called diffusion creep. In diffusion creep, individual atoms, oxygen atoms, silicon atoms, magnesium atoms, the building blocks of the olivine crystal, move through the crystal lattice one by one, migrating from regions of high stress to regions of low stress, the way a crowd slowly redistributes itself in a large room, not by anyone suddenly running, but by each person shifting slightly to fill the available space, over and over, until the whole distribution has changed. Each individual atom moves a tiny distance, summed across trillions and trillions of atoms, across the vast bulk of the asthenosphere, across millions of years, the rock has moved. Diffusion creep is the quiet, patient variety. It operates most powerfully at very high temperatures and in rocks with relatively fine grains, where the shorter distances between grain boundaries mean the atoms do not have as far to travel. The second variety is called dislocation creep, and this one involves not individual atoms moving through the crystal, but the movement of those defects, the dislocations, the tiny faults in the otherwise orderly crystal lattice, the places where a row of atoms is incomplete or shifted half a step out of register with the rows above and below it. A dislocation can move through a crystal the way a wrinkle moves across a carpet when you push one end of the carpet across a room. You do not pick up the whole carpet and slide it. You push, and a wrinkle forms, and the wrinkle travels across the carpet to the far wall, and then the carpet has moved. The wrinkle is the dislocation. It does the work. In dislocation creep, these defects move through olivine crystals under the vast, sustained pressure of 150 kilometres of rock above them and the sustained heat of a mantle that has been cooling, very slowly, since the earth was new. The dislocations travel. The crystal deforms. The rock flows. Both of these mechanisms, diffusion creep and dislocation creep, operate in the asthenosphere, and the balance between them depends on conditions the rock is experiencing: temperature, pressure, grain size, the presence or absence of water. Together they produce what we measure from the surface as the asthenosphere's defining characteristic, its defining property, the thing that makes it the weak sphere, the hidden cushion, its viscosity. Viscosity, you know this word in the kitchen. Honey has high viscosity, it flows, but reluctantly, slowly, pooling in a jar, running off a spoon in a thick and lazy ribbon. Water has low viscosity, it pours, it splashes, it runs easily, syrup is between them. And the asthenosphere has a viscosity that is so far removed from any of these that the comparison almost collapses under its own scale. The viscosity of the asthenosphere is estimated at somewhere between 10 to the 19th and 10 to the 21st Pascal seconds. Pascal seconds are the unit scientists use to measure viscosity. Water, for reference, has a viscosity of roughly 1/10,000th of a Pascal second. The asthenosphere, then, is somewhere between 100 million trillion and 10 billion trillion times more viscous than water. Not millions of times, not billions, 100 million trillion times or more. A number so large it loses meaning in the ordinary world, a number that requires the comfortable shelter of scientific notation to even write down without the page becoming absurd. And yet it flows. This is the thing, trillions upon trillions of times more viscous than water, and it flows. Slowly, yes, at rates measured in centimetres per year, in millimetres per decade, in distances no human instrument of the ancient world could have detected. But it flows. Because viscosity is not the same as impossibility. It is only a measure of resistance. Given enough time, and the Earth has time in amounts that make even the largest human number feel like a rounding error, given enough time, even a material of almost unimaginable viscosity will move. Glaciers move. Rocks, down in the warm dark, move. The ground is not fixed. The ground has never been fixed. It is only fixed on the timescale of a human life, the timescale of a civilization, even the timescale of a species. Expand the clock far enough, let the years accumulate into millions and then hundreds of millions, and the distinction between solid and fluid begins to blur and then to dissolve, and the rock that is undeniably, measurably, stubbornly solid on a human night turns out to have been, on the Earth's own unhurried reckoning, flowing all along. There is something genuinely restful in this, if you let it settle. The ground beneath you tonight is solid in every sense that matters to you. You could press your hand flat against it, and it would not give. You could stand on it, build on it, walk on it in the morning, and nothing would betray what is happening far below. The solidity is real, and so is the flow. Both are true, and they are not in conflict, because they operate on different clocks, and we happen to run on the short one. The rock is solid on our clock. The rock flows on its own. You can hold both of those things gently in your mind at once as you lie here, and let them coexist. But there is a layer still to add to this picture, a refinement that makes the asthenosphere something stranger and more specific than just hot rock that creeps. Because the mantle deeper below the asthenosphere is also hot rock. The mantle below, the lower mantle, is also under enormous pressure and enormous temperature, and yet it is stiffer than the asthenosphere, harder to flow, more resistant, a slower river. Something makes the asthenosphere specifically weak, specifically ductile, specifically the cushion it is. And that something turns out, when you trace it carefully, to be two things working together, two ingredients that conspire to push the rock of the upper mantle right to the edge of its own melting point, and keep it there, in that strange borderland where solid and liquid exist at once. The first ingredient is heat. We have been speaking of it as if it is simply a given. It is hot at 150 kilometres, yes, clearly, but it is worth holding the number still for a moment. 1,300 degrees Celsius. This is roughly the temperature of the outside of a high-bypass jet engine at full thrust. It is the temperature at which most steel becomes fully liquid. It is a temperature no sustained life could exist at, no technology of the surface world could comfortably operate in, a temperature so far from the conditions of the world you live in that it belongs more naturally in the vocabulary of an industrial smelter than in a description of the ground beneath a quiet house on a still night. And this heat is not coming from anywhere new. It is not the afterglow of a recent event. It is the residual heat of the Earth's formation 4.5 billion years ago, supplemented and maintained by the slow decay of radioactive elements, uranium, thorium, potassium, scattered through the rock in trace amounts, their nuclei quietly unstable, releasing tiny packets of heat as they decay, as they have been decaying since before the Earth was fully formed, and will continue to do so for billions of years to come. The mantle is a slow furnace. It is fueled by its own atoms, and it keeps the asthenosphere hot enough to sit, trembling, at the edge of its melting point. But heat alone would not be quite enough. The solidus, the temperature at which rock begins to melt, is not a fixed thing. It shifts. It depends on pressure, which rises with depth. And it depends on something else, something counterintuitive, something that took scientists a long time to appreciate fully. Because it is not what you would think to look for in a rock that is glowing dull red in the dark at 1300 degrees, under the weight of 150 kilometres of stone. It depends on water. Not liquid water. There is no liquid water at that depth, at that temperature, at that pressure, but water as a chemical presence, as a constituent locked inside the crystal structure of the olivine grains themselves. A few tens of parts per million, a few hundreds of parts per million, at most. To put that in terms that carry some texture, if you took the olivine of the asthenosphere and laid out 1,000,000 atoms of it in a row, perhaps a few tens of those atoms, or a few hundreds, would be hydrogen atoms that have bonded into the crystal structure and altered its chemistry. The rest would be the ordinary olivine. And yet those few, those tens or hundreds of atoms in 1,000,000, change everything. Water inside a mineral crystal, what geochemists sometimes call nominally anhydrous minerals, meaning minerals that do not officially carry water but turn out, on close inspection, to carry small but significant amounts. Water inside an olivine crystal weakens it. It weakens the bonds between atoms. It makes diffusion easier, makes dislocation movement easier, makes the crystal more willing to deform, more willing to creep. And crucially, it lowers the solidus. It lowers the temperature at which the rock begins to melt. In the dry rock of a deeper layer, a temperature of 1300 degrees might not be enough to produce any melt at all. The rock would remain entirely solid, still creeping by solid-state mechanisms, but with no liquid fraction whatsoever. Add a trace of water. Add, alongside it, a trace of carbon dioxide, another volatile compound that finds its way into the crystal structure of mantle minerals in small amounts. And the solidus drops. It drops enough that at 150 kilometres, at the pressures and temperatures that exist there, a tiny fraction of the rock does something it would not otherwise do. It melts. Not much. This cannot be said too carefully. Not much at all. The estimates, and these are estimates, because imaging the interior of the Earth with the precision needed to count droplets of melt between mineral grains is not a thing we can do directly, not yet, perhaps not ever. The estimates suggest a melt fraction of well under 1% by volume, up to perhaps a few percent in richer zones. Imagine, again, that 1,000,000 atoms of olivine. Perhaps several thousand of them, perhaps a few tens of thousands, in the most melt-rich patches, are no longer in a crystal. They are liquid. They have crossed the solidus, become melt, and they are sitting not as a pool, not as a lake, not as anything that remotely resembles what you might picture when you hear the word molten, but as films, as coatings, as a glaze, thinner than the skin of a soap bubble, smeared along the boundaries between mineral grains, threading its way through the interstices of the olivine crystal aggregate, the way dew sits on a spider's web, touching every strand, connecting everything, but adding no real bulk, no real volume, nothing you could scoop up or pour. These grain boundary melt films are the partial melt of the asthenosphere. This is what was mapped in 2023 as a nearly global layer. This is the molten component in the hidden cushion, not a sea, not a river, not even a visible wetness, if you could somehow hold a handful of this rock in your impossible hand. A thin glaze of liquid connecting the solid grains, invisible at any human scale, present in amounts that would register as a trace impurity in almost any other context, and yet important enough, and globally widespread enough, and newly mapped in enough detail that its discovery reshaped the conversation about what the asthenosphere is and what it does. And the olivine around those tiny films of melt, the vast, solid, dominant bulk of the rock, is glowing. At 150 kilometres, at 1300 degrees, the peridotite is hot enough that if you could somehow bring a sample of it to the surface instantly, holding its pressure and temperature intact, it would glow dull red, the red of cooling embers, the red of the bottom of a furnace. The same mineral that a jeweller cuts and polishes and sets into a gold ring as the gem peridot, that pale green stone, cool to the touch, catching the light on someone's finger, that same olivine, at depth, in the dark, in the heat, glows. It does not know it is also a gem. It does not know it is also, somewhere up at the surface in the thin, cold air, considered beautiful. Down here it is simply old and hot and slowly flowing, grain by grain, dislocation by dislocation, atom by atom, through the dark. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. So we have the mechanism now, laid out as carefully as it can be laid out in words, in the quiet of a night like this. The asthenosphere flows because it is hot enough to sit just at the edge of its own melting point, made a little hotter in effect, a little more willing to yield by a trace of water and carbon dioxide lodged in its olivine crystals. It flows by solid-state creep, atoms migrating through crystal grains, dislocations threading through olivine lattices, the rock deforming without breaking, yielding without liquefying, moving without any of the drama we usually associate with movement at the planetary scale. Its viscosity is astronomical by any human measure, and it flows anyway, because the Earth has time that makes even the most patient human waiting feel frantic by comparison. And through that creeping, yielding, gently deforming rock, threaded along the boundaries between its mineral grains like dew on a web, runs the partial melt, the whisper of liquid that the 2023 study found to be not a regional curiosity, not a local anomaly, but a nearly global presence. A film of partly molten rock at roughly 150 kilometres depth, running beneath plate after plate after plate, beneath the Pacific and the Atlantic, beneath the old stable cratons of ancient continents and the young spreading ridges of the ocean floors, a shared underlayer beneath almost everything. Earlier studies had seen hints of this melt, detected it in patches, debated how widely it extended, argued about whether the seismic signature they were reading was truly melt or simply hot rock or water-weakened rock, or some combination of effects that only looked like melt from the surface. The imaging was imperfect. The signals were ambiguous. The interpretations were many. And so the picture remained patchy, uncertain. A melt that might be widespread, but could just as easily be local, a feature of certain regions, certain tectonic environments, certain geological histories, rather than a global constant. The 2023 study by Junlin Hua and Karen Fischer and Thorsten Becker and their colleagues at the University of Texas Institute for Geophysics and Brown University compiled a global dataset of seismic measurements, the kind of measurements we will come to in a moment, the echoes of distant earthquakes read at stations spread across the surface of the Earth, and processed them with an eye not to any single region or any single plate, but to the whole world at once. The result, published in Nature, was a map. Or not quite a map in the ordinary sense, not a map you could hang on a wall and point to countries on, but a global picture of where, at the base of the tectonic plates, the seismic signal showed what the researchers interpreted as partial melt. And the picture showed it almost everywhere. Not everywhere, without exception. The distribution is not perfectly uniform. The melt fraction varies from place to place, is thicker or thinner or richer or poorer depending on local conditions, the temperature of the mantle there, the age of the overlying plate, the water content of the local rock, the distance from a spreading ridge or a subduction zone. But the overall picture, the finding that emerged from all the data combined, from hundreds of measurement stations and decades of accumulated earthquake recordings processed and compared, was of a layer that is, in broad terms, global, widespread shared, a film of partial melt at 150 kilometres depth that underlies not just some plates in some regions, but the plates in general, the world's tectonic plates as a class, as a collective, as a system. This was unexpected. Or it was more than expected, it was more continuous, more persistent, more genuinely worldwide than even those who suspected it to be widespread had assumed. The partial melt at the base of the lithosphere was not a regional irregularity. It was a feature of the planet. And then came the twist. And the twist is worth holding gently, because it is the kind of finding that quietly upends a long-held picture without making any dramatic announcement, without arriving with sirens or headlines or the kind of fanfare that attaches itself to more immediately spectacular discoveries. The twist arrived in the same paper, in the same dataset, as a statistical result that the researchers noted carefully, that the lead author described in plain language in the press release from the University of Texas, and that, once you have heard it, changes the way you hold the whole story. The amount of detected partial melt across all those plates, across all those measurement stations, across the global picture that the study had compiled. That amount, that melt fraction, that measure of how much of the grain boundary space between the olivine crystals has been replaced by liquid, does not correlate with how fast the overlying plate moves. The plates that sit above more melt do not move faster than the plates that sit above less melt. The plates that sit above less melt do not move more slowly than those above more. The melt fraction and the plate speed, when you plot them against each other across the full global dataset, do not show the relationship you would expect if the melt were the thing doing the lubricating. If the molten cushion were truly the grease in the bearing, the oil in the engine, the thing that allows the plate to slide, then more of it should mean a faster plate, or at least a looser, easier moving plate. And less of it should mean a plate that grinds more slowly, that faces more friction, that has to work harder to move at all. But that is not what the data shows. What it shows is the melt, more or less everywhere, in similar amounts, beneath plates that move at very different speeds, beneath plates that are nearly stationary, and plates that are among the fastest on Earth. The Pacific plate moving at something like 10 centimetres per year, and some of the old continental plates barely creeping at a centimetre or less, both with melt beneath them. neither significantly more nor significantly less than the other. The melt is there, global and consistent and real, and the plates are moving at their own different speeds, regardless of how much melt sits beneath them. The correlation is not there. The relationship that would justify calling the melt the lubricant, the engine, the reason, is not there. The conclusion, as the researchers stated it, is careful and measured in the way scientific conclusions are always careful and measured, hedged with the appropriate qualifications and the appropriate acknowledgement of what the data can and cannot establish. But the conclusion is clear. The partial melt does not appear to influence large-scale mantle flow. It does not appear to be the primary cause of plate motion. The asthenosphere is weak, yes, its weakness is real, its role as the low-viscosity cushion on which the plates ride is real, but that weakness is set mainly by temperature and by the water content of the olivine, by the same solid-state creep mechanisms we have been tracing through the dark, by the position of the rock relative to its own melting point. The melt that forms there, the thin global grain boundary film that the 2023 map traced across the base of the world's plates, is a byproduct of those conditions. A consequence. A passenger. Not the engine. The lead author framed it plainly, in the way you say something when you have been working on a problem for a long time and finally have an answer that surprises even you. The melt, he said, turns out not to influence plate motion. The assumption that had been sitting, mostly unexamined, beneath the popular picture of the asthenosphere as a lubricating molten layer. That assumption, tested globally for the first time with a dataset large enough to give the test real power, does not hold. And so the hidden cushion is real, and the partial melt is real, and the global film at 150 kilometres is real, and none of it is the story we were told. Not in the dramatic way the classroom picture was wrong. Continents floating on a sea of lava, the asthenosphere a molten ocean. But in a subtler, stranger, more interesting way. The melt is there, thinner and more ghostly than we imagined, a glaze rather than a sea. The weakness it sits in is real, but it is not caused primarily by the melt. And the plates glide across this layer at the pace of growing bone, for reasons that come, it turns out, not mainly from the soft cushion below them, but from something happening at the other end of the plate entirely. Something cold and heavy and descending, which we have not yet reached, which is still waiting for us in the descent ahead. But that is the next part of the story. For now, in this part, it is enough to rest with the picture we have assembled, the olivine crystals glowing dull red in the dark, the atoms migrating through their lattices in the slow, patient democracy of diffusion creep. The dislocations threading forward like wrinkles crossing a carpet, the trace of water and carbon dioxide whispering the solidus down just far enough that a thin film of liquid forms between the grains, and the whole vast, slow, globally consistent layer sitting beneath the plates like something placed there by a process too patient to be in any hurry, too large to be in any one place. Too old to be concerned with the brief urgency of anything that lives on the surface above it. It flows. It has always flowed. It will still be flowing long after every name we have given it has been forgotten and replaced by other names in other languages. Or perhaps no names at all. The weak sphere, the asthenosphere, the hidden cushion, whatever you call it. And whatever you picture when you try to imagine it, it is there, beneath this night, beneath your weight on the bed, beneath the foundations of the house, beneath the city or the countryside or the coast, 200 kilometres down, give or take, lost in the dark and the heat and the pressure, carrying the plate above it forward at a speed so slow it would take a very careful scientific instrument many years to confirm the movement at all. Let that be the image you carry into sleep, if it comes for you now. Not fire, not drama, not a molten sea churning and heaving beneath a thin crust of stone, but something quieter and stranger than that. A rock that flows, a solid that creeps, a crystal that yields, grain by grain, atom by atom, dislocation by dislocation, through the deep time hours that the earth counts instead of seconds. And threaded through it, thinner than you could imagine, a nearly global film of something that is, in the most technical sense, melted, barely, partially, ghostly, present everywhere and determining nothing. A passenger on a journey whose engine, it turns out, lies somewhere else entirely. There is still the question of how we know any of this, how we see a layer we can never drill to, how the map of 2023 was made at all, the seismic story, the earthquake echoes, the strange and indirect art of reading the interior of the earth in the slowing of a wave. That is where we are going next. And it begins, as so much of the story of the deep earth begins, with a trembling of the ground that happened very far away, felt faintly at a station on the other side of the world, recorded on a drum of paper or a digital sensor, and read with the patience that the planet, if not the people, has always had in abundance. The question of how we know anything at all about a layer we cannot reach is one of the quieter marvels of modern science, and it is worth dwelling in for a while, because the answer is stranger and more beautiful than you might expect, and because the knowing itself, the act of hearing the interior of the earth by listening to the echoes of its own violence, is as strange a feat as any the planet has to offer a person lying still in the dark. We cannot drill there. That is the first thing to understand, and it matters more than it might seem on the surface. The deepest hole ever bored into the earth, the Kola superdeep borehole in the far northwest of Russia, reached a little over 12 kilometres down after 2 decades of effort. And it stopped there not because the engineers ran out of will, but because the rock at that depth had become so hot, around 180 degrees Celsius, that it behaved more like a plastic than a solid, and the drill hole simply closed around the drill. 12 kilometres. The asthenosphere begins at around 80 to 200 kilometres down, depending on where you are standing and what lies beneath you, and it extends deeper still. The gap between what we have managed to pierce with metal and what we are trying to understand is not a small one. It is the difference between scratching the paint of a wall and reaching the foundations of the building below it. And yet we know the layer is there. We know approximately where it begins and where it ends, in broad strokes. We know that something changes in the rock at that depth, something that distinguishes it from the stiffer stone above and the denser, more resistant stone below. We know the temperature approximately, we know the viscosity in orders of magnitude. We know now that a film of partial melt runs through much of it at around 150 kilometres down, nearly worldwide, a discovery that was only confirmed to that degree of global continuity in 2023. And we know all of this without having put a single instrument anywhere near it, without a single core sample pulled from those depths, without a single direct measurement of the kind a laboratory on the surface would recognize as ordinary. We know it because the earth shakes. Not here, necessarily, not close. The shaking that matters most for this particular kind of knowledge is the shaking that happens very far away, on the other side of an ocean or on the far side of a continent, or in a subduction zone thousands of kilometres distant, and travels through the interior of the planet and arrives hours later as the faintest of tremors, almost imperceptible, registered not by a person standing in the street, but by a sensitive instrument buried in a quiet place, and connected to a recording device that preserves the shape of the vibration in fine detail. That instrument, in earlier decades, was a seismograph, and the record it kept was a line drawn on a rotating drum of smoked paper, and the line's small deflections told trained readers something about the nature of the ground the wave had passed through on its way from where it began to where it ended. Seismology is, at its core, the art of reading the Earth's interior in shadows and echoes. Earthquake waves, there are several kinds, and they behave differently, and that difference is part of what makes them useful, spread outward from their source the way ripples spread from a stone dropped in still water. Except that these ripples travel in 3 dimensions through the whole volume of the planet, bending and reflecting and slowing and speeding as they encounter materials of different density and rigidity. Because rock of different compositions and different temperatures transmits waves at different speeds, a sensitive enough instrument on the far side of the globe can tell you, by measuring when the waves arrive and how their shape has changed, something about everything those waves passed through on the way. This is the principle on which our knowledge of the deep earth is built. The mantle is invisible to every other tool we have at this scale, but it is not silent. Benno Gutenberg understood this. Gutenberg was a German-American seismologist working in the early and middle decades of the 20th century, and he spent much of his career reading those drums of paper, measuring arrival times, comparing records from different stations, building up a picture of the Earth's interior from the faint and patient language of waves. He found many things. But one of the things he found, and which bears on the story we are telling here, was a zone somewhere in the upper mantle where the seismic waves, specifically a type called P waves, the compressional waves, the ones that move fastest and arrive first, slowed down. They slowed measurably, not dramatically, not by half. Not enough that a casual observer glancing at the record would have seen it immediately. But measurably, in the careful statistical accounting that Gutenberg spent years building, the waves were travelling more slowly through a band of the upper mantle than they were through the material above it or below it. The rock at that depth was, in some sense, less stiff, less resistant, less able to transmit the sharp compressional force of a seismic wave at full speed. Gutenberg called this the low-velocity zone. This is the ELVs, those 3 letters that appear throughout the technical literature on the asthenosphere, and whose meaning is exactly as plain as the name implies. A zone, where the velocities are low, where something in the rock has softened enough or changed enough to slow the passage of a wave. And the boundary at the top of this zone, the interface between the faster transmitting lithosphere above and the slower transmitting asthenosphere below, carries Gutenberg's name in the technical literature as well. The Gutenberg discontinuity, sometimes abbreviated simply as the G. In the shorthand of people who spend their days reading seismic records, marks the base of the rigid plate, the ceiling of the soft cushion, the line where the mechanical character of the mantle changes from locked and stiff to creeping and yielding. This was a remarkable thing to discover in an era when many scientists still doubted that continents could move at all. Joseph Barrell had named the asthenosphere in 1914, reasoning from gravity measurements and the behavior of the ground under loading that there had to be a weak layer beneath the rigid crust. Reasoning, in other words, from the mathematics of how much the crust bent and rebounded under weight, not from direct observation of any kind. And now Gutenberg was finding a seismic signal that corresponded, at least approximately, to where that weak layer ought to be. The waves were slowing. Something down there was different. But what? What exactly makes the rock of the asthenosphere less able to transmit a seismic wave than the rock of the lithosphere above it? This is a question that has occupied seismologists and geophysicists for decades, and it is worth sitting with for a moment, because the answer, or rather the several competing possible answers, leads directly to the partial melt, to the grain boundary films, to the 2023 map, to the genuinely unsettled debate about how much any of it matters. A seismic wave moves faster through rock that is stiff and cold and tightly bound. It moves more slowly through rock that is hot or that contains any material that is not perfectly solid, or that has a different density, or that is organized in ways that resist the wave's propagation. The asthenosphere, we now understand, is hotter than the lithosphere above it, approaching or reaching the Cis-1. 300 C that sits near the melting point of peridotite at those pressures. That heat alone would slow a wave somewhat. The presence of even a trace of liquid, even a fraction of a percent of genuine melt, would slow it further, because liquid rock transmits seismic waves very differently from solid rock. And there are other possibilities too, subtler ones, elevated water content in the olivine crystals, or effects at grain boundaries even in the absence of melt, or temperature effects that fall short of any melting at all. The low-velocity zone could, in principle, be explained by any one of these factors, or by some combination of them. And separating them, deciding which is dominant and which is secondary, has been one of the persistent puzzles of mantle geophysics. The signals we receive at the surface are integrated over large volumes of rock. They do not come with labels. A wave that has slowed cannot always tell you precisely why it slowed, whether the cause was a degree of temperature, a pore of melt, a molecule of water dissolved in a crystal, or some combination of all three. This uncertainty matters, and it is worth holding in mind, because it is part of what makes the 2023 study significant. Not just what it found, but how it was able to find it, the method, the scale, the particular type of seismic data that the team led by Junlin Hua at the University of Texas Institute for Geophysics, together with Karen Fischer at Brown University and Thorsten Becker, assembled and analysed. Before we get to what they found, it is worth understanding what they were looking at. There is a particular technique in seismology called receiver function analysis. The principle is elegant in the way that many good scientific methods are. It takes something you cannot avoid, a complication in the data that you might initially wish away, and turns it into information. When a seismic wave travels deep into the earth and then comes back up, reflected or refracted back toward the surface by a change in the material it encounters, it arrives at a seismic station carrying in its shape a kind of echo of every boundary it crossed on the way. The exact timing of the wave, the way its components have been separated and transformed, the relative amplitude of different parts of the signal. All of this encodes information about what the wave passed through and where it encountered changes. Receiver function analysis is a way of extracting that encoded information, of reading the echoes and working backward to reconstruct the structure of the material the wave traversed. It is, in a sense, an acoustic X-ray of the mantle. except that the source of the X-rays is not a machine in a hospital, but the planet's own seismic violence, earthquakes, happening somewhere in the world, as they always are, and sending their signals outward in all directions, to be caught and read by every seismometer that can register them. The practical limitation of this technique, for a long time, was scale. A single seismometer gives you information about a relatively narrow slice of the mantle beneath it. A network of seismometers gives you more. But to map the base of the plates globally, to say with any confidence that the partial melt is not a local feature of a particular region, but something found almost everywhere, you would need a global dataset, assembled from the records of many thousands of seismic events, processed through thousands of individual receiver function analyses, and synthesized into a picture coherent enough to see. That is what the 2023 study did. Hua, Fischer, Becker, and their colleagues compiled records from stations across the world, processed them through receiver function analysis at a scale that had not been attempted before, and built from those echoes a map of the lithosphere-asthenosphere boundary across most of the planet's surface. And what the map showed was not what the earlier, more limited data had suggested. Earlier thinking, the picture that had prevailed before this study, treated the partial melt in the asthenosphere as something patchy and regional. It was understood to be present in some places, beneath the spreading ridges of the mid-ocean floor, where hot material was rising and decompressing and producing magma. Melt was expected and found. Beneath hotspots, beneath volcanic regions, melt was not surprising. But the idea that a coherent, continuous film of partial melt ran beneath nearly all of the tectonic plates, everywhere, not just in the tectonically active zones, but beneath the quiet old hearts of the continents as well, that was not the consensus picture. The receiver function data said otherwise. The 2023 map showed a nearly ubiquitous zone of partial melt at approximately 150 kilometres depth, underlying the plates as a near-global feature, not confined to ridges and hotspots, not patchy and intermittent, but something far more continuous and widespread than had been thought. The film is thin. The melt fraction is small, the dossier is explicit about this, and it deserves emphasis, because without it, the image in the mind reverts to the classroom cartoon of a lake of liquid stone. The melt fraction is commonly estimated at well under 1% by volume, and even generous estimates rarely go much beyond a few percent. This is not a lake. It is not a pool. It is not even a thin sheet of liquid in the way you might visualize a layer of water between stones. What it is, instead, is something closer to this. Imagine a mass of tightly packed mineral grains, each a tiny crystal of olivine, pressed together at depth and at temperature, and at the boundaries where two grains touch, at the very thin. Nearly two-dimensional interfaces where one crystal meets another, a film of material that is, in the technical sense, liquid. Not the crystals themselves, not the bulk of the rock, but the boundaries, the seams, the interfaces. A glaze, a coating so thin that it would be invisible to any instrument less sensitive than the ones geophysicists use to interrogate the structure of rock at the nanometer scale. This is what partial melting means in practice, at these depths and these temperatures. The rock is solid. The crystals are solid. The bulk mineralogy is solid peridotite, as it has always been. But at the grain boundaries, at the margins where the crystals meet, conditions of temperature and pressure and dissolved volatiles, water, carbon dioxide, have conspired to produce something that is not quite solid, that is just barely molten, that crosses the threshold of the solidus not in a dramatic sense, but in the most marginal and delicate of senses. A whisper of liquid, a ghost of a melt, present everywhere, and yet accounting for less than 1% of the total volume of the material. It is easy to understand why this is hard to see, and it is worth understanding why it matters that it is there at all, why a fraction of a percent of liquid, distributed as thin films across grain boundaries in a vast body of otherwise solid rock, would change the seismic properties of that rock enough to be visible to a wave passing through it from thousands of kilometres away. The answer lies in how seismic waves interact with the material they travel through. A wave moving through a perfectly solid crystal lattice is like a sound moving through a taut wire. The vibration travels cleanly and fast, because the material resists deformation efficiently, and the wave's energy is not absorbed or scattered. But a grain boundary that contains even a thin film of liquid changes this. The wave encounters, at the scale of the crystal, an interface where the material is less stiff, where some of its energy can be transferred differently, where the sharp compressional force of a P-wave is met not by the elastic resistance of a solid, but by the different and less efficient response of a near fluid. The wave slows, not dramatically, but measurably. And the more grain boundaries there are, the more continuous and connected the film of melt is, the more pronounced the slowing becomes. This is why even a fraction of a percent of melt can create a seismic signal detectable from the surface. The effect is amplified, in a sense, by the geometry. The melt is not in lumps. It is distributed as the most efficient possible network of interfaces, spread across the maximum possible number of grain contacts, and even a tiny total volume of liquid organized this way influences the behavior of waves far out of proportion to its quantity. And so the low-velocity zone, the signal that Gutenberg found, the slowing that has anchored discussions of the asthenosphere for most of a century, is, at least in part, a signal of these grain boundary films, of this whisper of melt, of this nearly invisible fraction of liquid distributed through a vast body of otherwise solid rock, at a temperature close enough to the solidus that the distinction between solid and not quite solid has become fragile, contingent, maintained only because the pressure is high enough and the water content is low enough and the conditions are just exactly as they are and not otherwise. The 2023 map made this concrete in a new way. By showing that the melt-associated signal is not a regional feature but a global one, it suggested that the partial melt at C50 km depth is not an anomaly of particular tectonic settings, but something close to the normal state of the upper mantle at that depth. Wherever there is an asthenosphere, and the asthenosphere in some form is a nearly universal feature of the mantle beneath the plates, there is this film. It is part of what the layer is, not an occasional visitor, a resident. And yet, as we will come to, the same study that established this near global continuity also found something that complicated the simple story. But that is part 4. For now, the layer is there. The map is made. The echoes have been read. It is worth staying for a moment with the fact that all of this knowledge, this map of a film of partial melt 150 kilometres down, this reconstruction of the base of the tectonic plates across most of the globe, was made entirely from the echoes of distant earthquakes, recorded by instruments at the surface, processed through mathematics and inference, and the patient accumulation of thousands of individual measurements. We did not go there. We cannot go there. Every number in this picture, the depth, the temperature, the melt fraction, the extent of the film, was derived from something that happened far away and far above, and worked backward to the layer by people with training and patience and the specific kind of intelligence that is comfortable reasoning about what you cannot see from the shadows of what you can. This is not unusual in science, but it is worth noticing. The interior of the Earth is one of the least directly accessible places in the known universe. We have sent instruments to the surface of Mars. We have imaged the event horizons of black holes. We have measured the temperature of the cosmic microwave background radiation with high precision. And yet, the mantle beneath your feet, at a depth that an airplane could reach in minutes if the airplane could somehow survive the temperature and pressure, remains a place we know only by inference, by the language of waves, by the slow and patient accumulation of evidence from things that shake. There is something appropriate about that, for the purposes of tonight. The unknowing has its own texture. The knowledge that is built from echoes and shadows and inference has a different quality from the knowledge that is built from direct observation, not less reliable necessarily. Because the mathematics of wave propagation is well understood, and the seismic data is real, and the receiver function analysis is sound. But different. More like listening to a story told through a wall than reading the text directly. You are confident in the broad outlines and less certain about the fine details, and the layer itself remains perpetually out of reach, doing what it does in the dark and the heat and the pressure, indifferent to the efforts of the people above it to understand it. The Gutenberg discontinuity, that G, marks the ceiling of the asthenosphere and the floor of the rigid plate above it. The plate above it, the lithosphere, is defined not by any difference in the kind of rock, but by a difference in behavior, in temperature, in the particular relationship between the rock's condition and the mechanical forces acting on it. Above the G, the peridotite is cool enough and stiff enough to behave as a rigid plate, to transmit stress across its width, to fracture cleanly when pushed beyond its limits, to carry the weight of mountains and ocean floor over geologic time without significantly deforming. Below the G, the same peridotite, chemically similar, mineralogically recognizable, has crossed a thermal threshold and begun to flow. The threshold is approximately 1300 degrees Celsius. Not a sharp line in practice, not a wall that the rock crosses all at once at a particular depth, more of a gradual transition where the viscosity of the material decreases and the stiffness falls and the ability to sustain long-term stress without flowing away becomes increasingly compromised. The rock above is cold enough in relative terms to be solid in every practical sense, to hold its shape over the timescales relevant to us, to the mountains above, to the oceans, to the history of human civilization. The rock below is hot enough that given enough time, enough of the deep time that the earth counts instead of seconds, it will flow. The lithosphere-asthenosphere boundary, the lab in the literature, is defined by this transition, and what makes it strange and interesting and worth emphasizing is that it is a boundary between two things that are chemically nearly the same. Cross the lab, and you do not cross into a different rock type. You do not cross from granite to basalt, from one mineral assemblage to another. You cross from one thermal state of peridotite to another. The olivine above the lab and the olivine below the lab are the same mineral, the same green crystal, the same chemical composition, the same lattice structure. But the olivine below the lab is hot enough that it flows, and the one above is not. This is the crux of the story of the asthenosphere, the fact that the name, Coined by Joseph Barrell in 1914 from the Greek for weakness, tried to encode before the theory of plate tectonics existed to give it full meaning. The weakness is not a different material, it is the same material in a different state. The boundary is drawn in temperature, not in chemistry. The plate and the cushion beneath it are, at some deep level of description, the same thing. The same rock, the same mineral, the same composition of the upper mantle, differentiated only by how hot they are, by how close they sit to the solidus, by whether the thermal conditions are enough to have produced that thin film at the grain boundaries that makes the difference, seismically, between faster and slower, between stiffer and more yielding, between a rigid plate that carries a continent and a soft cushion that lets it move. All of this, the lab, the elves, the grain boundary films, the global map, was assembled from shaking. From the trembling registered at a distant station, from lines on paper and signals on sensors and the slow, careful mathematics of people who have spent their careers reading the language of waves. The 2023 receiver function analysis by Hua, Fischer and Becker was a culmination of this tradition. Not the invention of a new method, but the application of an established one at a global scale that had not been attempted before. Drawing on the accumulated seismic record of many decades, the records of many thousands of earthquakes, processed and integrated into a picture that no single earthquake and no single station could have produced alone. The picture showed the melt. Widespread, presenter near global film at around 150 kilometres depth. Not the patchy, regionally concentrated feature that the older, more limited data had suggested, but something continuous and nearly planetary. A shared underlayer, present beneath the young ocean floor of the spreading ridges and beneath the old, thick roots of the continental cratons alike, differentiated in detail, but present as a feature almost everywhere the receiver functions looked. Earlier studies had found partial melt in tectonically active regions and had cautiously suggested it might exist more broadly. The 2023 study confirmed the breadth of it, the near universality. And in doing so it changed the picture of the asthenosphere from a zone that is partially molten in some places and largely solid in others, to a zone where the melt, thin and ghostly as it is simply part of what the layer is. The word film is the right one to hold in mind. Not a layer in the sense of a visible stratum, not something you could point to on a cross-section and say, there, that stripe of red is liquid rock. The melt fraction is too small for that, well under 1% by volume in the standard estimates, up to a few percent in the most generous readings. What this means in practice is that if you were somehow to take a cubic kilometre of the asthenosphere at 150 km depth, which you cannot, but imagine it, and somehow separate the solid rock from the liquid would fill a space smaller than 1% of the original volume. A trace. A residue. The thinnest of glazes, distributed across the grain boundaries of an enormous mass of hot solid rock, present in the way a light frost is present on a field, coating surfaces, following the geometry of the crystals, sitting at the interfaces, rather than in the way water is present in a lake or even in a wet sponge. And this film, this frost-like, grain boundary glaze, is detectable from the surface, because seismic waves slow when they pass through it, because receiver functions, analysed carefully, show a change in the character of the mantle at that depth. Because Gutenberg's low-velocity zone, identified in those early careful readings of the seismograph drums, turns out to correspond, at least in significant part, To a nearly worldwide coating of partial melt on the boundaries between olivine grains, at a depth of roughly 150 kilometres, maintained by the combination of the mantle's heat and a trace of dissolved water and carbon dioxide that just barely keeps the solidus low enough for a fraction of the rock to cross it. The whole map of the deep earth is written in echoes of violence that happened far away. The knowledge is indirect and real. The layer is unreachable and known. The melt is invisible to any direct instrument, and yet its presence, its near-global presence, confirmed in 2023, has been established as firmly as any knowledge derived from inference can be established, which is to say, with appropriate uncertainty about the details and with considerable confidence about the broad picture. It remains for us to consider what the film is doing down there, whether it matters to the motion of the plates, whether the cushion is the engine or merely a passenger, whether the weakness of the asthenosphere is a product of the melt or of the temperature and water content alone, the melt being a consequence rather than a cause. These are the questions that the 2023 study raised as much as it answered, the counterintuitive finding at the heart of it, the one that complicated the simple story and opened the genuinely unsettled debate that the scientific community is still working through. But that is the territory we enter next. For now, let this be enough. A map made from echoes. A film discovered in the shadows of waves. A layer that we know is there at 150 kilometres because distant earthquakes told us so, in a language of timing and slowing that took a century of patient reading to decode. The earth is quiet above the passages. The waves have long since passed through, registered, been read. The instruments continue their patient watch on every continent, waiting for the next distant trembling to bring them another message from below. And the film itself, that grain boundary glaze, that whisper of partial melt at the base of the rigid world, persists in the dark and the heat, present everywhere and yet accounting for almost nothing by volume, coating the olivine crystals with a patience that makes human patience seem like a brief, excited breath. And so we arrive at the counterintuitive heart of it. The finding that the 2023 study left behind, once the mapping was complete and the data had been read, and the distribution of the film had been charted across the globe, was not the one most people would have expected. The finding was this: the amount of partial melt detected beneath a given plate does not predict how fast that plate is moving. When Junlin Hua and Fischer and Thorsten Becker and their colleagues at the University of Texas Institute for Geophysics and Brown University ran the numbers, the correlation was not there. The melt and the speed of the plates did not track each other. They did not rise and fall together the way a cause and its effect ought to. The cushion was everywhere, yes. The film was nearly global, yes. But the plates above it moved at their own pace, indifferent to how much or how little melt lay below them. This is the kind of finding that is easy to state and difficult to absorb, so let us stay with it for a moment, in the slow way the night deserves. The assumption that had rested beneath so much of the popular understanding of plate tectonics, the assumption that the molten layer was the lubricant, the thing that allowed the rigid plates to glide, the agent of motion, that assumption now required revision. Not because the layer was not there. The 2023 study confirmed it was there, more completely and more continuously than had been demonstrated before. But being present and being in charge are two different things, and the study found that the layer, wherever it was thicker, wherever it carried more melt, wherever the partial melting was most pronounced, was not producing faster plates. The plates above those melt-rich patches were not speeding up. The plates above the relatively melt-poor patches were not slowing down. The correlation simply was not there. The lead author framing, quoted widely from the University of Texas release, was that the melt turns out not to influence plate motion. A plain statement, a quietly unsettling one if you had spent any time with the picture of continents sliding gracefully on a hidden molten sea. The sea is there. It is just not steering the ship. What this means, mechanically, is that the weakness of the asthenosphere, its capacity to yield, to let the rigid plates above it drift, is governed primarily by something other than the melt. The two properties most likely to set its softness are the temperature and the water content. The heat, which keeps the rock near its melting point and makes solid-state creep possible. And the water, those few tens to hundreds of parts per million, locked invisibly into the olivine crystals, lowering the solidus and softening the grain boundaries without ever producing a pool of liquid you could see or touch. These are the controls. The melt is a byproduct of them, a consequence of being hot and slightly damp at 150 kilometres depth, not the ingredient that makes the asthenosphere what it is. Think of it this way. If you heat a stick of butter near a warm lamp, the butter softens before it melts. The softening happens because the temperature has climbed toward the melting point, because the molecular structure has grown easier to deform, because the solid has become ductile. And if a small patch of the butter then melts and becomes liquid, that liquid does not suddenly become responsible for the softening of the rest. The softness was already there, in the heat, in the temperature, in the approach toward the phase boundary. The melt is a marker that the temperature has arrived. It is not the cause of the approach. The asthenosphere, in this reading, is the warm butter. The melt is the small spot that has gone entirely liquid. The spot tells you how warm the butter is. It does not make the butter soft. This is what the 2023 study pointed toward, that the partial melt is, most likely. A signal of the conditions rather than a creator of them. An indicator. A consequence. Present because the temperature is high and the water content is sufficient, not present because the plates required it to be there. And yet, and here the story opens one of its genuinely unresolved doors, not everyone in the scientific community reads the data the same way. The question of how much the melt truly matters remains actively debated. Some researchers, working from other studies and other imaging methods, argue that melt-rich patches can locally change the behavior of the layer, that in specific regions or at specific depths, a higher concentration of melt might provide something closer to genuine lubrication, reducing the friction between the plate and the mantle beneath it. The 2023 global analysis found no statistical support for this at the planetary scale, but the planetary scale is precisely that, a global average, a broad pattern, and the behavior of any one subregion might differ from the average while still leaving the average unchanged. Science works at multiple scales simultaneously, and the answer that holds at one scale may not hold at another. What can be said with confidence is that the question is genuinely open. It has not been settled. The 2023 study made a strong contribution to the debate, perhaps the strongest contribution in a generation, by demonstrating for the first time just how continuous and widespread the melt film actually is, and by showing that its variation does not track plate velocity. But contribution to a debate is not the same as closing it, and the researchers themselves were careful about what they claimed. The film is there. The correlation with plate speed is not. The causes of the low-velocity zone, whether from small melt fraction, from elevated water content in the olivine, from grain boundary effects at elevated temperature, from the combination of all of these, are still being weighed. Science at its frontier always looks like this: a clearer view of the terrain, and a sharper understanding of which parts of it remain unmapped. So then, if the melt is not driving the plates, what is? The honest answer is that the plates move the way they do because the Earth is, at its deepest level, a heat engine, and the plates are part of how it moves that heat. The same convection that keeps the asthenosphere hot, the slow churning of the mantle, heat rising from the core and from the decay of radioactive elements, cooler material sinking, the whole interior turning on a clock measured in tens of millions of years, that convection is part of the system. But even convection is not quite the complete picture, because the most powerful force that has been identified as a driver of plate motion is something more specific, more mechanical, and in its own way more elegant. It is called slab pull. When ocean floor, that dense, cold, basaltic rock that makes up so much of the plate's surface, when that ocean floor reaches the end of its long journey across a basin and begins to descend back into the mantle at a subduction zone, it sinks. It sinks because it is cold and dense. Because a plate that has spent tens or hundreds of millions of years drifting across the surface has cooled, contracted, grown heavier than the hot mantle below it. And as it sinks, as the leading edge of the plate dips down into the deep mantle and continues to fall, it pulls the rest of the plate behind it. It drags the plate forward. The weight of the descending slab, falling through rock that is softer and hotter than the slab itself, exerts a tension on the plate above and behind it, hauling the whole structure toward the subduction zone. The image that captures this best is something from an ordinary kitchen. Imagine a tablecloth laid across a smooth table, with one edge hanging over the side. The hanging edge is heavy enough, eventually, to begin to slide off, and as it slides, it pulls the rest of the cloth after it, slowly at first, then faster, the weight of the falling portion dragging the flat portion across the table's surface. The slab is the falling edge, the plate is the tablecloth. The mantle is the table, smooth enough at the right timescale not to stop the motion. This is the dominant engine. Cold, dense, ancient ocean floor, returning to the deep. The plates do not need to be pushed from below so much as they are pulled from ahead. The slab pull is the largest single force in the ledger. There is also ridge push. At the mid-ocean ridges, where new seafloor is created, where hot mantle material wells upward, cools, and becomes new ocean floor, the elevation of the ridge itself, the slight topographic high of fresh, hot, buoyant rock, exerts a gentle outward push on the plates as they move away. Think of it as the starting slope. The plate at the ridge is elevated compared to the plate farther away, and gravity encourages it to slide downhill, away from the ridge, toward the distant subduction zone. Ridge push is real and contributes to the motion, but it is a smaller force than slab pull, a background contribution to a system whose main driver lies at the other end of the journey. And there is basal drag, the coupling between the base of the plate and the mantle beneath it. The friction and shear of one material moving relative to another. Where the mantle is actively convecting, where it is rising or sinking, it can exert a dragging force on the plate above, assisting or resisting the motion depending on direction. Basal drag operates through the asthenosphere, through that soft and yielding layer, and its contribution to the overall motion budget is still being quantified and debated. It is part of the system. It is not the whole of it. What emerges from all of this is a picture of whole mantle convection, a planet-wide circulation of rock driven by heat from the core and from the interior, pulling plates downward at subduction zones, pushing new material upward at ridges, and carrying heat toward the surface over timescales so vast that the word long becomes inadequate. The asthenosphere sits within this system as its softest and most yielding zone, the layer that accommodates the motion, that allows the rigid plates to slide above it without locking and seizing. That provides the mechanical decoupling between the hard crust and the deeper mantle. It is essential to the system. Without it, without a zone soft enough to allow the plates to drift independently of the deeper rock, the whole arrangement of moving plates and spreading ridges and subducting slabs might not be possible in the way we observe it. But essential and driving are different roles, and the 2023 study suggests that the asthenosphere, in the form of its partial melt at least, is playing the first role rather than the second. It is a passenger in a vehicle it makes possible. There is something almost philosophically satisfying about that if you allow yourself to sit with it long enough. The thing that enables the journey is not the thing that drives it. The road allows the travel, the soft layer permits the drift. But the power comes from elsewhere, from the cold weight of descending slabs and the patient heat of an interior that has been losing warmth since the planet formed 4.5 billion years ago, and has not yet finished. And through all of it, the plates move at their glacial pace, 1 to 10 centimetres a year. The Pacific plate is among the fastest, crossing the ocean basin at a rate that could, given enough time, carry a continent from one side of the world to the other. Other plates move more slowly, but none of them are still. And the unit of measurement that captures this speed best, the one that has stayed in the scientific literature as both accurate and useful for conveying the scale of it, is the growth rate of human fingernails. Your fingernails grow at roughly 1 to 10 centimetres a year, depending on the nail and the person and the season. They grow in the dark, quietly, without effort, at a pace you never notice, except in accumulation. And the plates move at the same pace. Not as a metaphor, not as an approximation chosen for convenience, as an accurate comparison of two real rates arrived at independently. In the time it takes you to fall asleep tonight, a tectonic plate will move something less than the width of a single hair. In the time it takes a hair to grow long enough to need trimming, a plate will have moved about a centimetre. In a human lifetime, a plate moves roughly as far as a tall person is tall. In 1,000 years, it moves the length of a city block. In 1,000,000 years, it moves perhaps 10 kilometres, and in 100 million years, it moves 1,000 kilometres, which is how ocean basins open, how continents separate, how Pangaea became the scattered geography you would recognize from a school atlas. The motion is happening now. It is happening as you lie still. Beneath the floor, beneath the bedrock, beneath the sediment and the basement rock, and the upper crust and the lower crust, the lithosphere is drifting, the asthenosphere is yielding. The film of partially molten olivine is coating grain boundaries in the dark, and the slab somewhere distant is falling, pulling the plate forward by a distance you would need a very precise instrument to measure in a single year. The Earth is not still. The Earth has not been still for 4 billion years, and yet it feels, from where you are lying, like the most solid and permanent thing in existence. This is the paradox that the asthenosphere resolves if you hold both parts of it at once. On the timescale of a human life, the rock is solid. You could quarry it, build with it, stand on it for a century and feel nothing move. The atoms do not flow on a human clock. The mantle does not ripple like water when you press your hand to the ground. It is, to every instrument of human experience, rock, dense, resistant, permanent. But on the Earth's own clock, the same rock is a river. The same olivine crystals that feel like stone to a geologist's hammer are, over 10 million years, creeping slowly through their positions, diffusing along grain boundaries, allowing the whole mass to deform, to flow, to carry heat upward and cold downward, and the plates above them across the surface. Solid and fluid are not opposites. They are descriptions of the same material at different timescales. Ask the rock what it is over a weekend, and it says solid. Ask it what it is over 100 million years, and it says a very slow river. This is what physics calls a non-Newtonian fluid in a broader sense, what geologists call a viscoelastic solid, what most people simply cannot quite picture. Because the two descriptions, solid stone, flowing river, seem incompatible. But they are not. They are the same material answering a different question. And the asthenosphere is where that paradox is most legibly written, because it is the zone where the rock is closest to its melting point, where the creep is fastest relative to the surrounding mantle, where the transition between rigid and flowing is most pronounced. The viscosity, that measure of how resistant a material is to flowing, how thick it is, how reluctantly it gives way to force, runs between roughly 10 to the 19th and 10 to the 21st Pascal seconds in the asthenosphere. Numbers on that scale are difficult to relate to. But consider, water has a viscosity of about 1,000th of a Pascal second. Honey has a viscosity of perhaps 10 Pascal seconds, a very thick industrial oil, perhaps 1,000. The asthenosphere is, by these numbers, more than 1 trillion times more viscous than water, more viscous than anything you have ever touched or poured. So viscous that a human observer watching it for an entire lifetime would see no movement at all. And yet it flows. Given the timescale the Earth operates on, it flows. The 1 trillion times thicker than water rock yields to the weight above it, to the heat within it, to the patient geometry of the planet's interior, and it creeps, steadily and without urgency, carrying continents as it goes. This is the genuine strangeness of the deep Earth. Not the spectacular strangeness of lava fountaining from a volcanic cone, or the violent strangeness of a fault line releasing centuries of accumulated tension in a single terrible minute. Those are real, but they are the exceptions, the acute episodes in a story that is mostly written in the slow. The deep strangeness is quieter. It is the strangeness of rock that is also a river, of solid that is also fluid, of a planet that looks from outside like a still blue sphere and from inside is slowly, patiently churning. The partial melt film at 150 kilometres is part of that strangeness. It is the mark on the thermometer that tells you the temperature, without being the temperature itself. It is the condensation on the outside of a cold glass, telling you something about the conditions inside without being the cold drink. It is real, and it is nearly everywhere, and in 2023 a group of patient seismologists at 2 universities compiled enough data to see it for the first time as a continuous global feature rather than a patchy and regional one. And then they found, to their credit, and perhaps to their own surprise, that the thing they had mapped so carefully did not do the job that most people had assumed it was doing. The melt is there. The melt is not in charge. The weakness of the asthenosphere, its willingness to yield, its capacity to let the plates above drift at their fingernail pace, that weakness comes from heat and water, from the temperature that keeps the olivine close to its melting point without quite crossing it, from the trace of water dissolved invisibly in the crystal structure, lowering the solidus, softening the grain boundaries, permitting the creep that makes everything else possible. These are the genuine agents. The melt is their signature, not their source. And the plates themselves are pulled primarily by their own cold and heavy leading edges, falling back into the interior, dragging everything behind them with a force patient enough to rearrange the continents over 100 million years. The asthenosphere accommodates this. It makes room. It is soft enough at the right timescale to allow the plate above to move while the deeper mantle below moves at its own pace and in its own direction. The decoupling, the mechanical independence of the rigid plate from the convecting interior, is possible because the asthenosphere is weak. How weak it is, and whether the melt contributes to that weakness or is merely a consequence of it, is still being worked out. That is where the science stands. That is where the scientists are, working, attentive, reading the next set of seismic signals, designing the next analysis, asking the question again with better instruments and longer data records. The debate is not a failure. It is the sign of a field that is genuinely probing the edge of what can be known, using only the indirect evidence that a planet provides when you cannot dig past 8 or 10 kilometres into its surface. All of it is happening in the dark. The olivine crystals glowing dull red at 150 kilometres depth, coated in their near-invisible grain boundary films, creeping in the dark and the pressure. The seismic waves that have already passed through tonight, if any earthquake large enough has occurred somewhere in the world since you settled into this listening, have already threaded their way through the asthenosphere, registered their slight slowing, and arrived at some distant instrument array, carrying their message about the conditions below. The researchers who will eventually read those signals may not do so for months or years. The signals are patient, they wait, and the plates above all of it continue their imperceptible drift, carrying the land you are lying on a little further from wherever it was when you were born, a little closer to wherever it will be when the next 100 million years have turned. In your lifetime, the drift amounts to something like 3 to 5 meters, a short walk, a pace or two. Nothing you would notice in a landscape, nothing that would change a border or move a mountain. But 3 to 5 meters is real. The movement is real. The river below is real. You are not on solid ground in the way you may have always imagined. You are on a raft of rigid rock, thick enough to feel permanent, drifting across the surface of a planet that is, at depth, a slow and patient river of stone. Beneath the raft, the asthenosphere yields and creeps and accommodates. Beneath the asthenosphere, the deeper mantle turns on its own long clock. And at the heart of it all, the core delivers heat that has been making its way outward for 4.5 billion years and has not yet finished. This is the ground you are lying on. This is what the title promised to show you, and this is what the evidence, read carefully and honestly, reveals. Not continents floating on a molten sea. That picture was never quite right. But something stranger, and in its own way more beautiful. A solid earth that is also a slow fluid. A nearly worldwide film of partial melt that is a passenger in a system it did not build, and a set of plates drifting at the speed of growing fingernails above a cushion whose weakness comes from heat and water and the patient physics of crystals under pressure. The argument over how much the melt matters will continue. New seismic arrays will be deployed. New methods will refine the images. New studies will add their findings to the ledger, and the ledger will be revised, as it has been revised before, and will be revised again, because the planet is more complex than any single study can exhaust. That is not uncertainty to worry about. It is the ordinary condition of a field working honestly at the edge of what can be seen. What we know is enough to feel the scale of it and to feel it as something vast and calm rather than something alarming. The earth is quietly alive beneath you, has been for billions of years, will be for billions more. The motion is too slow to feel and too persistent to stop. The solid is also a fluid, the river is also a stone, and the cushion beneath the plates is real and nearly everywhere, whatever role it ultimately turns out to play. If you feel moved to share where in the world you are listening from tonight, there is a place for that in the comments, and those comments are read. The community of people who find their way to sleep inside stories like this one is scattered across every continent and every time zone, and it is a quiet comfort to know where each of them is lying, what the dark looks like from their particular window, what the stillness feels like in their particular part of the world. From a cold northern city where the winter is long, or from somewhere near the equator where the night stays warm, or from a house at the edge of a ridge where the geology underfoot is very old, wherever you are. The asthenosphere is beneath you at 150 kilometres, and the plates are drifting at their imperceptible pace, and the olivine is creeping in the dark. There are more stories here if you want them. Slow ones, careful ones, built from the same patient attention to what the evidence actually says, told at the same unhurried pace. They will be waiting whenever you need them. But for now, there is no more to follow. The map has been read, the film has been described, the debate has been laid out honestly, with its open edges intact. The engine has been named, and the passenger acknowledged, and the deep time paradox of solid stone and slow river has been brought, as gently as this subject allows, to the surface. The ground is still. Your breath is slow. The asthenosphere, 150 kilometres below wherever you are lying, is doing exactly what it has been doing for hundreds of millions of years, yielding softly, grain by grain, crystal by crystal, without hurry and without rest. History will still be here in the morning. For now, rest.